Hello, and welcome back to another episode of Sparky's Tech Corner. Now, I'm going to try to make this as simple and as brief as possible. This is my first time. Yeah, I forgot to switch over the speakers. Okay. Now, like I was saying, I'm going to try and make this as quick as possible just to go over what I'm doing on this. I figure I'd give live streaming this a chance to see if it's going to be any easier or faster compared to actually editing and going through Adobe Premiere. So basically what this is I've been working on a design for the Commodore 64 power supply, my own design. I have got some I've got some inspiration from different people off of the internet and YouTube. And I'm hoping that what I have will actually be pretty good and pretty interesting. So let's go ahead and go on a lowdown of the reason why I'm actually designing a new power supply. I've got a basic schematic brought up on the screen right here. And basically, the Commodore 64 power supply has two different inputs. We have a 9-volt AC input, and we have a 5-volt DC input. So, you gotta forgive me, my dog's running back and forth in the front room. Anyways, we got two different power outputs. We got a 9-volt AC and a 5-volt DC. Most of the electronics will be either AC or DC voltage for the intake on it. So, why does the Commodore 64 have these two different power outputs? Well, the computer uses the 9-volt AC as a system clock. He also uses the 5-volt DC as let's see here. Give me 1 second. Sorry about that. Anyways, what I was getting to, uses two different power outputs. It uses AC and DC. The AC is for the system clock, and the DC is for everything else on the computer itself. Now, the DC side is pretty simple. It's just got a single bridge rectifier going through a 3052 switch mode voltage regulator. We got two capacitors that help regulate the voltage ripple in the system to help stabilize the voltage down to 5 volts. Now, a lot of people ask, why would you want to design a power supply? Why can't you just use, the ones that came with it? Well, the original power supplies have a big issue with them. The main issue is they short out internally. And when they short out internally, usually what happens is this 9-volt AC line crosses over to the 5-volt DC. Or the switch mode regulator or the transformer goes out and shoots, 110 voltage from the wall outlet to the computer itself. And that pretty much fries the computer. I mean, the computer is fixable, but you gotta know how to fix it in order to get repaired. Uh, so the point is to have a power supply that has the right amount of power, safeguards in place on the supply to keep anything like that from happening. Now, how do we do that? Well, the design I'm going to show you will help dramatically with this. And the first part of this I'm going to show you, not that one, is going to be the legend I made for this. And the components I've gone is going to be the fuse, the varistors, bridge rectifier switches, potentiometers, coils, different solid capacitors, xenodiodes, grounds. This is a special type of surge protector. It's called a gas discharge tube. And these are just drawings illustrating like if I have a circuit having to jump over another circuit or two wires coming together to form a circuit, and basic signal for ground. We're gonna start with the wall side power, and basically how this is gonna work is we got a ground, off ground here. We got a hot line and we got a negative. Now, a lot of people go look at this and go, there's a lot of fuses in this. Well, I'm putting a lot of redundancy in this power supply, more than what you actually would need in any typical household electrical component. The reason why I did this is just it's not that expensive to do, and whether if it's redundant, whether if it won't ever go off, the protection's there. So we got a fuse on both the hot and the neutral side. And then we go down into this right here. This is my main first part surge protection. And it's the gas discharge tube. And basically how this works is once voltage in this line gets above a certain amount, kind of like, from a thunderstrike, these varistors will open up and allow that surge to go to this gas discharge tube. It is also connected to off ground as well. So when it opens up, it will have a direct path to ground. We also have varistors right here, and these varistors will help direct load instead of into the device itself. It will direct it back into itself and back through the system. So theoretically, when this system, if it ever gets hit by lightning, hopefully these fuses will pop, and before I can even get to the transformers, it will discharge itself for the ground on the gas discharge tube. And even if it gets past this point, we got another set of fuses here and another varistor here. So at least it will protect this part of the circuit for a time. Now we go to the transformers. Actually, no, beforehand, we got two capacitors here, and they just help stabilize the voltage ripple in the line, and that's basically all these capacitors here do. The coil also helps and aids in the stabilization of the ripple current in the AC circuit side. So we go to these two transformers here. These two transformers are pretty good sized, and they're a special kind of transformer. They're called an insulation transformer. So even if this system got hit by lightning, even if all these protections don't work. It's not going to get past this transformer because this transformer is designed as an insulation barrier and will not allow that high spike current to jump across into into the secondary socket. So even like no brownouts, anything like that, the secondary side of the socket is pretty much protected. So let's go ahead and go to the first primary side. And this is the first primary side up here. And that's this here. Now, this is the side that's for the Commodore 64. This is the side where the 110 wall voltage has got to get reduced down to 9 volts socket, 9 volt references. So we'll go out AC side first because that's a little bit simpler to explain. Like before, I have a fuse right in here. This design, well, no, I'm not even gonna do it. This one's just gonna have the one fuse in it. And we have a discharge arrestor too. So if voltage spikes above a certain amount here, it'll jump over this varastor into the neutral side of that socket. And basically what would happen is that voltage short will create a high enough amperage to pop this fuse, disabling this entire socket in case of some sort of a malfunction. And that's pretty much it for the AC side of the socket. That's one of the reasons why I chose this style transformer. Now we're going to go up to our DC side. Transform the 9 volts AC to 5 volts DC. We have our same socket protections, the fuse and the varastor. Same principle applies here. If any kind of voltage gets above a certain amount, we'll jump over this varastor, short out the socket, pop the fuse, disabling the entire socket. Now with that, we'll go through here and we'll start rectifying the power, basically turning our 9 volts AC into 9 volts DC. So right here is going to be our AC side, and right here is going to be our DC side. So as it goes through, it will direct what power it needs to go through its positive and its negative roots. We got 2 capacitors here, just as a type of filtering, because the more we can get the electricity goes through in wave currents. AC is constantly changing between positive and negative. DC, it's either one or the other. And we want to get these wavelengths stabilized as possible. That way, our bridge rectifier can actually do its job properly and doesn't have to work as hard. So once it goes through and does what it needs to through here, we'll have a positive side and then a actual negative side to this. Now, until we get through our actual voltage reducer here, it's going to be 9 volts until this point. So what we're going to do here is we're going to filter even more this power. So we got 2 sets of capacitors here, which will store up the power and help give a constant flow of electricity to kind of curve that waveform. Our coil here will also kind of merge the waveforms together. And then we'll go for a secondary capacitor. Hopefully by the time we get through this capacitor, our waveform is going to be a nice, straight, steady 9 volts. It's not going to get dipped down any kind of voltage, and it's not going to be all over the place. Hopefully we'll have a nice, smooth voltage by the time we get to this point. After that, we're going to go up to our actual voltage regulator. And this is actually a integrated circuit regulator. The way I'm actually designing this right now is to accept two different styles. This is the first style. The second one's gotta be I believe it's gotta be a TSR3. No, excuse me, I take that back. This is a TSR2. No, this is a TSR3. It's gotta be designed with a TSR2 too also. The only difference is with that one, you'll get rid of your potentiometer, and that's about it. That's all you have to get rid of because this potentiometer here is what actually adjusts the voltage on this voltage regulator here. This one allows for a little bit greater control, plus or minus, of the actual voltage output. The TSR2 doesn't. It's just straight 5 volts all the way, and will only utilize these 3 points. Now, once we go from there, we have a xenodiode. So any kind of interference that dips down to the negative, hopefully will get directed by this diode back to the negative side. And then we have one last capacitor for filtering method. And then hopefully we have a nice steady, nice solid, nice clean and filtered 5 volts going to a computer. So afterwards, that's pretty much it for this side of this circuit. Now, the secondary side for number 2 is pretty much the exact same principle, except for we're going to have 2 DC outputs, and we're going to have a bigger transformer. Instead of a 9-volt transformer, we're going to have a 15-volt transformer. Why? We need a 15-volt transformer because we're actually going to be putting out a 12-volt and a 5-volt DC output. This side of the power supply is going to be for the floppy disk drive for the Commodore 64. Now, it's the same exact principle. Go through, it has the socket protections, it has the capacitors to help filter out unwanted noise. We'll go for our bridge rectifier, turn out 15 volts to AC to 15 volts DC. We'll go through and we'll filter that out. We'll merge those wavelengths together a little bit with coil, filter it out some more, have a nice steady 15 volts, and both sides of these sockets are identical until we get to this point. And basically this point here, this is a 5-volt regulator, and this is a 12-volt regulator. From there, this is also designed the same way, to use the TSR2 or the TSR3. It's designed with the 3 because it's more complicated to install in, but it's also easier to use this design, and I can just put in a simpler design later if I need to. Again, a potentiometer to adjust the voltage out of these volt regulators. We don't use the TSR3, and we go with the 2. This circuit will be X-nayed, it won't even be needed. Again, xenodiode to help direct any kind of negative current on the positive side to the negative side, and a cap to help stabilize the voltage out. And this is pretty much the simplest way I can make this diagram right now. It is a lot more complicated than this. Again, I designed it to be very redundant. The entire system has about 8 different ways to protect the computer from any kind of a power surge, a brownout, or anything like that. My concept goes along the same as another concept on YouTube. I cannot remember the guy's name off the top of my head, but I'll put his name down in the comment in the description. Like I said, it's all to protect the Commodore 64 because these old power bricks are bad about shorting out. And the bad thing is you can't repair them too, because whenever they made these bricks, they fill the entire circuit board area with epoxy. So even if you could tear the thing open, you're not going to get to the circuit components because they're all covered in epoxy. I guess whenever Commodore was designing these things, they was intending on them running in the 21st century. So, besides from that, I see nobody's watched or nobody's came in and actually viewed it. Oh well. The video's gotta be up. I might leave this up for a couple days. I might decide to take it down and actually do an edited video. So with that, I'm gonna go ahead and let you go. Since there's no comments, I'm not gonna answer any questions. And I'll see you guys on the next one. Thank you.